Hey, this is Mr. Aiden. This is Chemistry Honors. This is chemical equilibrium. One of my favorite topics is called chemical equilibrium. It's one of the central topics of college or AP chemistry, and so that's why I like to go through it in Chemistry Honors to give you some background. And so this is an introduction on chemical equilibrium. The amazing thing is, I have, for the most part, built into you guys a misconception that almost all reactions go to completion. So you have A plus B and it yields some sort of product, okay? And so it's going to go to full completion, and that's just not correct. Is most reactions, especially in nature and the human body, are reversible reactions. They come to equilibrium. Whether it's your red blood cells and the ability to resist acids or bases, its change in acids or bases, it's called a buffered blood. Whether it's your metabolic pathways that are reversible, whether it's weak acids or weak bases, so many reactions are what we call reversible reactions. And so what I want to do is I want to take a look at a little bit of a way to look at this in terms of what's happening in terms of a model, what's happening in terms of a mathematical model, and then what's happening in terms of a graphical model. So I'm going to look at three different things. So you can see here I have what I'm going to call solution A, and I have solution B. You can see at the start of the reaction I have all A, I have 0 B. And so what's going to happen is this: A is going to transfer at a rate of 70%, okay, whereas B is going to transfer back at a ratio of about 10%. Okay, so in the very first, let's call it the very first minute, you can see A is going to transfer 70% of it. Okay, so it's going to go all the way down to here. And that makes B go up 70%. Okay? And so you can see we transferred 70%. We had 10 particles, 10 liters or whatever. It went down to 3, which meant this 7 went over here to 7. Now remember, what's going to happen is the B at the exact same time is going to transfer 10% back. Now B didn't have anything in it at the beginning, so it doesn't transfer anything back. Does that make sense? And so this is where we're at in the first minute. Are we at equilibrium or not? Now, equilibrium doesn't mean we have the same amounts. It means that my amounts are not going to be changing anymore. So here we go. Then the next minute, A is going to transfer 70% of what we have here and over to here. And remember, B is going to transfer 10% of what we have over here. Okay, so this guy is going to go down to about this. This guy goes up the same amount because it transferred. But remember, at the exact same time, B was transferring back 10%. Okay, and so this guy comes down to that. This guy comes up to that. Okay, we're still not at equilibrium because the concentrations are still changing. So this is where we're at after 2 minutes. After 3 minutes, this guy's going to transfer again. It's going to transfer again 70% of this. 70% of this, which means he's going to go down a little over 1. Okay, which means this guy goes up a little over 1. Okay, but at the same time, this one's transferring back 10%, which means he's going to go down about 0.8, which means he's going to be about 8.7 or so. This guy's going to be about 1 point. This guy's going to be about 1.3, and that's where we're at after 3 minutes. Fourth minute, this guy's going to transfer 70% over. Okay. Now, do you see how we're never going to get 0? Because every time we're transferring some over, we're transferring some back, aren't we? So we're going to transfer some more over. So we're going to transfer about 1 over. He's going to transfer about 1 over here. And then he's going to transfer back, which means he's going to transfer about 1% of this guy, or sorry, 10% of this guy, which means he's going to come back. And this guy's going to come back here. Do you see how the volumes are, they're not really changing a whole lot anymore. Okay? We end up transferring the exact same amount. So again, now the next minute, we're going to transfer some. We're going to transfer some. He's going to transfer some back. He's going to transfer some back. Do you see how the concentrations are not changing anymore, which means we are at equilibrium. Equilibrium doesn't mean we have the same concentrations. Equilibrium means that the concentrations are not changing anymore. Okay? So let's take a look at this in terms of, this was our chemical equilibrium demonstration. Different from some other demonstrations, but that was our demonstration of chemical equilibrium. So let's take a look at a sort of a mathematical demonstration. Remember, what did we say is A was transferring 70%, whereas B was transferring 10% back. So you can see A transferred 70%. What's 70% of 10? We're subtracting 7, which means as he subtracts 7, he's going to add 7. Okay? And then the B is transferring 10% back. What's 10% of 0? Well, 10% of 0 is 0. Which means he's going over here. So after the first minute, where are we? After the first minute, and I'm just saying minute as a unit of time, we have a concentration of 3. We have a concentration of 7. So this is where we're at 1 minute of time. Okay. Now the next minute, what's going to happen is beaker A is out of this 3, it's going to transfer 70% over. What's 70% of 3? Well, it's 2.10. So I'm going to add 2.10. And B is going to transfer 10% back. What's 10% of 7 is 0.70. So he transfers 0.70 back. What happens at the end of this second minute? At the end of the second minute, let's see. We had 3. We subtracted 2.0. We add 0.7. We're at 1.60. What happens with B? We have 7. We added 2.10. We minus 0.70. We're at 8.40. We are not at equilibrium yet. Okay, this is where we are after 2 minutes. Now, B is out of the 1.60. It's going to transfer 70% over. What's 70% of 1.60? It's 1.12. And we add 1.12. Okay. What's 10% of 8.4? It's 0.84. Okay, 0.84. And so at the end of the third minute, we have 1.60 minus 1.12 plus 0.84. That gives me 1.32. I'm trying to stay consistent. 1.32. And where are we here? We're 8.40 plus 1.12 minus 0.84, and that gives us 8.68. Okay, and so this is where we are after the third minute. 3 minutes. Okay, I'm going to move these up here if that's okay because I'm running out of some room. So I'm going to do beaker A. We're at 1.32. Beaker B, we are at 8.68. We're still not at equilibrium. So remember, he transfers 70%. What's 70% of 1.32? That's negative 0.92, which means we're adding 0.92 over here. What's 10% of 8.68? That's negative 0.868. Or I'm going to kind of round to 2 decimal places, which is what you're going to do. So what do we have? 1.32, negative 0.92 plus 0.87 gives me 1.26. My B, 8.68, adding 0.92, subtracting 0.87, which gives me 8.74. Sorry, I'm going to do this in red. I'm going to stay consistent between my A and my B just so that it helps you guys out. Thank you, Mr. Ayton. 8.74. Now, and that's where we are after 4 minutes, right? This is where we are after 4 minutes. Now let's take a look at the 5th minute. He's transferring 70% over. What's 70% of 1.26? That's negative 0.88, which means he adds 0.88. What is 10% of 8.74, that's negative 0.88, which means I'm adding 0.88. Do you see how what's happening? The amount that I'm transferring is the same here, right? Which means I'm going, actually that's 0.87 and 0.87, my bad. And what do we end up getting? We end up getting 1.25. And we end up getting 8.75. And that's where we are. That's where my concentrations are after the 5th minute. Now I want you to see what happens during the 6th minute. The 6th minute, I'm transferring 70% of the 1.25. What's 70% of the 1.25? It's negative 0.88, which means plus 0.88. What's 10% of my 8.75? Is negative 0.88. Okay, or negative 0.87 if I'm doing some rounding here. Which means what am I left with? 1.25 and 8.75. Do you see what's happening? Look at my concentrations. 6 minute. Take a look. After 1 minute, my 10 went down to 3. My 3 went down to 1.6. My 1.6 went down to 1.32. My 1.32 went down to 1.26. My 1.26 went down to 1.25. My 1.25, 1.25, 1.25, 1.25, 1.25. The concentrations are not changing anymore. And look at the B. The B went from 0 up to 7, up to 8.4, up to 8.68, up to 8.74, up to 8.75, 8.75, 8.75, 8.75, which means I am at equilibrium. If we look at it graphically, A started all the way up at 10, didn't it? A started all the way up at 10. After 1 minute, where was he? He went all the way down to 3. Can you believe that? Then he went all the way down to 1.6. Then he went all the way down to 1.32. I'm just taking the data that I had from before. Then he did 1.26. Then he went 1.25, 1.25, 1.25, 1.25, 1.25. The B started at 0. Then the B went all the way up to 7. Then he went to 8.4. Then he went to 8.68. Then he went to 8.74, 8.75, 8.75, 8.75, 8.75. If you take a look, this is going to be really hard for me. That is awful. That is absolutely awful. This is really going to be difficult. So he comes. Not bad. And this blue goes. Not bad. Okay. Do you see how this is really bad right here, isn't it? I'm going to change this guy. Oh, that's beautiful. Beautiful, isn't it? Do you see at exactly where were we when we hit equilibrium? If we come back, it was right around 5 minutes. Do you see at 5 minutes? This is when we are at equilibrium. This is when we are at equilibrium, chemical equilibrium. And you can see it's not when they're equal. It's not when it's not when they crossed. It's when these concentrations stop changing. That is when we are at equilibrium. And you can see, when are we at equilibrium? We're at equilibrium right there. We're at equilibrium right there, okay? Right when the concentration of the reactants and the products remain constant. That is definition number 1. Actually, it's number 2 of chemical equilibrium. But it's also when the rate of the forward reaction is equal to the rate of the reverse reaction. You can see how the reactants, the rate or the slope is really negative. Right here, the slope or the rate is really positive. Then the slope becomes less, the slope becomes less, the slope becomes less until the slope becomes 0. The slope is negative here, the slope is negative here, the slope is negative here. It's getting closer and closer and closer to 0. Once your slopes or your rates of the forward reaction is equal to the rate of the reverse reaction, that is when we are at equilibrium. Okay? Let me give you one last example of something at equilibrium. Okay? Let's just say we start with 50 moles of H2, 50 moles of N2, and nothing of the NH3. So the H2 starts at 50, the N2 starts at 50, and the NH3 starts at 0. And let's just say the H2 went down to 41 at equilibrium. So the H2 goes from 50, and I'm going to actually do this column in green, if that's okay. So it goes from 50 down to 41. Okay, how much did the H2 decrease by is 9 moles, or 9 molar, whatever you want to say in terms of its concentration. Well, take a look. This red value here, that is the change in the number of moles. So we want to take a look at the molar ratio. Look at the molar ratio. We have a 3 to 1 to 2 ratio. For every 3, we take away 1. For every 9, we take away 3, isn't it? 3 to 1, 9 to 3. For every 1, we gain 2. For every 3, we would gain 6. So you can see the 3 to 1 to 2 ratio, the 9 to 3 to 6 ratio, that is embedded in that change in the number of moles. Which means at equilibrium, this 50 went down to 41, this 50 went down to 47, and this 0 went to 6. Okay? So what happened here is the 50 went down to 41. Okay, the 50 went down to 41, which means it went down. That was the H2. The nitrogen went from 50 down to 47. That was the N2. And the NH3 went from 0 just up to 6. And that was the NH3. And I hope you can see the change is the number of moles. There was only 1 mole change here, there was 3 moles change here, and there was 2 moles change here. And so as we take a look, that is chemical equilibrium. That's a great introduction to chemical equilibrium. Why? Because I did it, and just joking. It is a really good introduction to what you need to know about chemical equilibrium. We're going to keep going as we go forward in learning about this amazing subject, which has so many implications on life. Thanks, guys. Do your self-assessment for chemical equilibrium. Bye-bye.